To lecture 10. And again. Yeah. So we will now move towards algorithms for optimization. We'll do a bit more on convexity, minima, and Lipschitz continuity. We'll be spending actually some time on Lipschitz continuity, which is very critical to get intuitive understanding on why algorithms would converge and also formally prove their convergence. Okay, so we'll spend some time on Lipschitz notion of Lipschitz continuity. Well, I say Lipschitz continuity, well, Lipschitz continuity and smoothness, I must add here. They're related concepts. Before we move on to yeah, algorithms. So these are topics done so far. We talked about some local and global minimum conditions, and largely we talked of sufficiency conditions here. We'll also look at some necessary conditions, but necessary conditions are things that directly follow from your basic discussion on calculus. Sufficiency is what also characterizes convexity, so it's important. Sufficiency driven by convexity. So we did that, and we did talked about strict convexity in unique minimum. I'd left you a homework problem to understand. I had already proved it in the class, but develop maybe finer understanding of why convexity leads to global minimum. Strict convexity leads to unique global minimum. I give a very broad overview of constrained convex problems, and we'll maybe delve into it later on, and then really move into algorithms. Towards algorithms, we'll need to understand Lipschitz continuity and Lipschitz smoothness, along in conjunction with strong convexity, which we have already done. Okay, so yeah, so we already discussed how subgradients are related to minima. A zero subgradient is a sufficient condition for global minimum, right, for a convex function. For a convex function, zero subgradient is sufficient for global minimum. We did this. We did this as a sufficiency condition. Um, I'd give also suggested that you look at a little bit more beyond what we have discussed. So how do you really characterize the existence of global minima, right? As global minimum always exists. We had presented this Weierstrass theorem. The convex function is there and it is non-empty and bounded, has bounded sublevel set L alpha, then F has a global minimum. But yeah, I'd given that as a homework problem. But let's try and develop a little bit more understanding. If we did this, that critical points of convex functions are global minima. This is a sufficient condition. Okay, and that's what we used to also show the conditions for the global minimum of this function, right? We derived the global minimum for the lasso kind of problem and motivated again the iterative soft thresholding algorithm. Okay, but then we'll try and understand this notion of saddle points. Okay, saddle points are interesting when you especially start talking about global minimum, local minimum, and their connection. So one way of looking at saddle points is that the gradient vanishes, but x, that point at where it vanishes, is neither a local minimum nor a global local maximum nor a local minimum. You have all seen a horse saddle, right? In the next slide, I'll be showing you a horse saddle, which is very characteristic. One side you move, you basically get increasing values of the function, or gradient rather, a curvature upwards. Another side you move, you start seeing curvature downwards. Okay, that is a basic notion of a saddle point. Let's move on and understand the notion of a saddle point in the single dimensional case. Here's the non-convex function 3x raised to 5 minus 5x cube. Okay, and this has the derivative f dash x is 15x square x plus 1 into x minus 1. You can factorize it. So the critical points, if you look at this, the critical points correspond to um, this part. X plus 1, set it to 0, you'll get minus 1. You set x minus 1 to 0, you'll get 1. And finally, if you set x square to 0, you'll get 0. Of the three, the sign of f dash x changes at 1 and minus 1. That they are the local minimum and maximum respectively. So let's try and understand with respect to this image. Okay, so at this point in red here, you have this is 1. Right here, the sign of f dash x changes. Okay, let's highlight this in blue. At this point, again the sign of f dash x changes. This is the point minus 1. Okay, when you say sign of f dash x changes, basically you're saying that it's in one case it's curved upwards, f dash is increasing, it's convex. Other case f dash is decreasing, is concave. Okay. F dash is decreasing in this case, whereas in this case f dash is increasing. The sign, of course, doesn't change at 0, all shaded in yellow. So this is neither a local maximum nor a local minimum. So this function is not convex everywhere. Convex functions won't have such saddle points, right? Or convex regions of functions won't have such saddle points. But we see that for non-convex regions, you can have such saddle points. Okay, non-convex or non. When I say non-convex, I mean non-concave either. Okay. With this note, yeah, if you have questions, please do ask. The function is not convex. Yeah. Let's look at a function. Actually, you can think of a simpler function as well, x1 minus x2 square. This is slightly more complex. So x1 square minus x2 square, you'll find similar behavior. What happens in this case is that this is of course slightly more complex. It seems to have some points which appear like a point of sitting in a horse saddle. So if you look at this curve, say consider this curve. This is horse saddle here, and what do you observe here? A local max along this. This is a local maximum along this curve. On the other hand, at the same point, I'm sorry, I should have shown not this one. I meant this point, yeah. So this is a saddle. That's not a saddle, yeah. So if you see here, at the point at the corner sitting here, or you can also consider a point here, right? That's also will be our saddle. Let's yeah, I can consider this point. Let's say this point. So it's a local max along this curve, whereas at this point, but along this curve you have a local min. Yeah. So this along this curve you have a local min. So again, this is an example of a saddle point. Lots of analysis in the deep neural network right arena is often about saddle point analysis, and saddle points cannot be dismissed of, because as you know, in convex regions these saddle points will talk about a local minimum. In concave regions it's a local maximum, right? So these, I mean, what are these points of zero gradient? Saddle points in general are those where they can be along one direction a local minimum, and along another direction a local maximum. Any questions, let me know. So yeah, I'll just make a note here that lots of analysis in the deep neural network regime is about saddle point optimization. All I'm trying to say is they're not necessarily bad. Okay. So then the global minimum, does it always exist? That's where I had left off our discussion in the last class. I said, it'd be nice for you guys to think a little bit more on this front. I mean, I gave this example of e raised to x, right? So now e raised to x is convex, and it's actually bounded from below, but the bound is never achieved, right? The bound is 0, but it's never achieved. This curve here. So Weierstrass theorem comes to a rescue and says that um, if there is a non-empty and bounded sublevel set, now does L alpha, such a non-empty and bounded sublevel set, exist here? Well, no, right? It's unbounded below. For any value alpha, if you take the sublevel set is unbounded below. It has no boundary. It just keeps extending and extending. Oh, in this case, by Weierstrass theorem doesn't look like there needs to be a global minimum, and in fact it doesn't have a global minimum, point of global minimum. Okay, so since f is continuous, it retains a minimum over a closed and bounded, that is compact set at some point x star. So x star is also a global minimum, right? Because f of x star is less than or equal to f of x for all x in L alpha. And since f of x star is less than or equal to alpha, it follows that for any x in which is not in L alpha, it must be that f of x is greater than alpha, which is greater than or equal to f of x star. Okay, so this if it attains a minimum, that is the bounded part which you talk about here, bounded at some x star, then x star will be a global minimum. Okay. And general, I can just I'll just try and for this. Okay, so this is the case we are talking about. That there is some boundary. This is a set of the points x. Okay. And what we are trying to say is that this there will be some kind of x star where the minimum is attained because it's a boundary, corresponds to a boundary, closed bounded set will have this boundary, right? That boundary will be defined by x star. Any other thoughts you have as homework, I mean contemplation, do let me know, otherwise we'll proceed.
Sir?
Yeah.
Sir, am I audible?
Yes, yes, you are audible.
Sir, I was thinking, does existence of minima imply boundedness of sublevel set?
That's a good question. So this doesn't imply the other way. Just because f has a global minimum doesn't necessarily mean that um, it must have a bounded sublevel set. Though in most cases you'll find it happens. Okay, the global minimum gives you that bounded sublevel set, but it's not an if and only if condition. Good question. Do you have a counter example in mind?
No, sir, I couldn't think of any. That's why I was asking.
Right. Even I'm not able to think of one easily. I don't think there are any easy functions. So there'll be some contrived problem, but it doesn't hold because there exists one. Yeah, even I'm not able to recall offhand the exact form of such a function. Anyone else?
Like if the global minimum is strict and the function is differentiable, we can prove that all the sub-level sets would be bounded
Ah,
because
if it's a
this loop.
strict global minimum, you're saying if it's strict,
Yes, if
it's
it's a
unique,
strict loop.
and the function is differentiable.
Yes,
Okay, let's
like
let's make that claim. Um, I mean, function is differentiable in addition to it being convex, etc. Like, it was okay. So I would like you to think about it, and I mean, if you have a proof, why don't you post it on the group, right? Any other thoughts? Okay, let's move on otherwise. So this is a general convex optimization problem. Minimize fx subject to x in some x where the x is a convex set. This calligraphic x is the convex set. If of course calligraphic x is the entire domain, it becomes an unconstrained optimization problem. Now the function f need not be convex everywhere. That's the other point we've been making. You could have saddle points. Okay, relaxations. What you generally don't want to relax is the constraint set. But so relaxations are typically on the function f. Need not be convex everywhere. But as you must have figured out, convexity even locally is important, though it might be convex in some regions. Okay, now the entire deep learning is also hinged on convexity. I'm claiming that. Why? For example, if you have a deep network, right, multiple layers. So this is one layer, this is another layer, and this is our final layer. And imagine that I was talking about fully connected, but you could also think of, um, you could think of CNN, sparse connections, and so on, right? If now I froze all the weights except the last layer weights, let's say these are the last layer weights. So the function viewed only as a function of the last layer weights in most settings will be convex. So that's what the region, that's the notion of a region we are talking about. Some regions. Okay, an example of the regions. Region could be defined as that where you know in which all weights, or rather defined as the region of last layer weights for a deep NN, right? That is with all other weights, layer weights frozen. Okay, that's a classic example of a sum region. Let me know if you have questions here. So you will relax, but typically you will not relax the set itself. So these are fine. Typically you don't relax the set. You had a question? So when we say convexity of the set, we also mean convexity of the constraint set. Is typically not relaxed because then you can't move comfortably within the search space. Okay, a special case. I mean, this is what I was alluding to. A special case is when here you have gix less than equal to 0, where gi's are convex functions. So these are like sublevel sets at sublevel no, alpha value 0. HIs being affine functions. Again, that's an example of convex set. So these are typically convex sets. Okay, any question? And in the case of how do you deal with optimization, right? For example, if you're in the interior of the X, then 0 belonging to the subdifferential is sufficient. So if say X is in the interior of this calligraphic X or X star, right? Then we would expect that 0 belonging to the subdifferential of F at X star is sufficient. But the issue is what happens when you're dealing with something on the boundary, right? So let's try and visualize this. When we say typically convex set, what does it look like? Okay. When I say something is greater than less than equal to 0, so you could actually visualize this whole thing as intersection of half spaces. Okay, so like even a simple example here. Okay, so each of these is like saying less than equal to 0, less than equal to 0. So each of these is basically like this black curves giving you a green region. Okay, so giving you a green region. Sorry. So this is giving you green region. Likewise, each of them will give you some green region. I mean in the interior basically, entire thing. But then bounded by another such hyperplane, or another such inequality. This is how it looks like. There'll be gaps, holes here, of course. Um, some regions will be dense because they're they're kind of part of many such regions. I mean, obviously, all of them should satisfy, but they might be directly connected to more such regions. Okay, so it's in principle what's happening is you have intersection of there's a dual description, intersection of multiple such half spaces using supporting hyperplanes, or so any convex set could be defined using such infinite inequalities. Okay. Back the dual description for convex sets them to be specified as intersections of such inequalities. We have seen this duality come earlier. Now the dual description of sets also is being looked at here. Okay. So this is think of this GI is intersection of sublevel sets which are convex. Okay. These are nothing but yeah, intersection of convex sublevel sets. And they're actually zero sublevel sets of GIs. Any questions here? So what happens when you try and apply these constraints? I mean, it's also possible that P could be zero, M could also be zero, P could also be zero. Okay, that's the other point here. Either or both of M and P could be zero. That means you're dealing with no inequality, no constraints at all. Special cases. I mean, and if you look at HIX, again you're talking about intersection of affine sets. So how do you characterize optimality condition for such constrained optimization case? So instead of saying the gradient goes to zero, what we'll say is the dot product between the gradient and any point x minus x star, a solution, must be greater than or equal to zero. Okay. See, of course, you think of this in cases, right? So simpler case for this is when you're dealing with uh, a point in the interior, right? Case one is let's say x star is in the interior of x, calligraphic x, or this capital X. So if it's in the interior, then it's very simple. 0 belongs to the subdifferential of f at x star, or in this case, or more specifically, you can say if it's differentiable, then like saying a gradient of f at x star is vanishing, and this holds. This is a sufficient condition. Let me just move this below. This is a sufficient condition, and as a result of which this will hold. Um, if one of them is zero, obviously the dot product will be greater than or equal to zero, and that's fine. The interesting part is when the case two, which is when it's on the boundary. Okay, so case two is say this. In this case, what happens is um, x star is in the boundary. So boundary can also be denoted by partial, but I don't want to confuse you, so I'll just say boundary. Okay, and then we are saying that x minus x star should form an acute angle with the gradient of f at x star. Okay, so this again should be easy to see. This is of course showing the view in the x space, but you can also have a similar kind of view in the function space. Okay, so this is the original input space, but here's a function space view where basically you're saying that this if this x star, or let's take this red example right here. Now if you had a constraint, right, and let's say the function was behaving like this, the green was the function and you have this red point sitting at the boundary, x star, the boundary. So then what we are saying is the direction of the gradient. Obviously now you have to go back to the input space x, is forming an acute angle. Basically we are saying that there's no way we can move within the region and for example increase the value of the so this is talk about minimization, Right? So suppose we were looking at um, yeah, this is actually looking at a maximum. Sorry, here in this case we're looking at maximum. But in any case, what we are saying is we can't move within the region and yet uh, consistently improve on the function to be optimized. Okay. So yeah, if there are questions, let me know. So there are lots of constraint optimization problems: linear, quadratic. Objective is linear, objective is quadratic, but in all these cases the inequalities are intersections of half spaces, Ax less than equal to b. Okay. And specifically the QP is a convex optimization problem if and only if what? When would you say that this is convex? Any guesses? The linear problem is always going to be convex. Yeah. Yes.
When Q is positive somewhere.
Right. The Hessian of F, which is Q, is positive semi-definite. Right. Q is positive semi-definite. Now see, our discussion on the general constraint or convex optimization optimality condition was very preliminary. We'll delve on this a little later. But now I want to get equipped, even in the unconstrained case, how do you deal with algorithms and their convergence? So I'm a little keen to get to Lipschitz continuity, finish gradient descent analysis, Nesterov, and then after these we will revisit. So it's okay if you haven't gotten a complete hold of constraint case. After this, we will revisit the constraint case. Okay. So for the constraint case, I was saying that we will be invoking a notion of Lipschitz continuity. I'm giving some reference on Lipschitz algebra, both uploaded on Moodle. At the same time, you'll find a couple of other links. Now, you may wonder how this is all relevant for deep learning. Yes, it's all very relevant for deep learning. Um, and I've put a list of some papers. There are many more papers. Some of these papers which attempt to compute local Lipschitz constant of various deep networks. So yeah, you can have a look at it. And why are they important? We'll see soon. Okay. So with this, let's move on to Lipschitz continuity. So a function is Lipschitz continuous with a constant L if the rate of change of the function is in some sense upper bounded. Right? I mean, uh, one way of looking at the rate of change is rate of change. Okay. Can be roughly thought of as the absolute value of fx minus fy relative to the distance between x and y. Okay, so there you are saying that, well, this is less than equal to L. I mean, if you're allowed to divide by x minus y, that is when x and y are not the same, they don't coincide. So it's like a linearly scaled upper bound and the difference of function values at 2 points x and y. That's another way of looking at it, right? That is a linearly scaled upper bound, absolute value of the difference of function at points. Yeah. Any questions? So why are we interested in? See, strong convexity said that the function has at least some curvature. Convexity is okay, increasing values of the slope. Here we are trying to say, well, the function is not changing too fast. That's what we are saying. Rate of change is upper bounded. That is, the function is not changing too fast. Okay, so it's like saying that, okay, the import is too soon, too fast. Right, so that's how, it's limiting how fast the function changes. Now it turns out that there is a connection of Lipschitz continuity with the gradient. What is that? So you can, I mean, let's taking hint from what I did so far. Let's do the following. Let's try and write down the absolute value of the following. Limit as s tends to 0 of f of say x plus vh. X is a scalar or hv. V is a vector. Okay, minus f of x. Whole thing divided by h. So this is what? It's a directional derivative. Right? And if you try now write x as x whatever, and then y is x plus hv. Right? This is basically um, this whole thing is basically less than equal to L, and this is nothing but the directional derivative of the function f at x along the direction e. Okay. This is upper bounded by L. So now this is only for a differentiable. Okay, it doesn't necessarily always hold because we never assume that f is differentiable. So if this is if f is differentiable, again I want to emphasize that function f need not be necessarily differentiable. Therefore, we have to put this additional clause if f is differentiable. Only then. So if for this also means that for any unit norm vector v, the absolute value of the directional derivative along v is less than or equal to L. So yeah. So if there is a subgradient, okay, I just let me just take this entire description again on the next slide. The same thing. So you're saying if f is differentiable, then we can talk about the directional derivative. Otherwise, in general, you can also talk about subgradient, and the subgradient norm should be less than or equal to L. So we can, yeah, and all of us know that this directional derivative is nothing but the dot product of the gradient of f at x with v. So then you can basically use Cauchy-Schwarz and so on. Yeah. So let's move on to calculus properties. Some properties. What properties would you expect? I want to keep this a bit interactive. Okay, so I've given you some idea already. I mean, if you take sum of two functions, would it be Lipschitz continuous? Anyone? So F1 is L1 Lipschitz. and f2 is L2 Lipschitz. So then what can I say about f1 plus f2? Any suggestions?
Uh, we can show using the triangle inequality that it is L1 plus L2 Lipschitz.
Okay, great. Yeah, this is f L1 plus L2 Lipschitz. Good. Lipschitz continuous. I mean, I'm just using Lipschitz. It's Lipschitz continuous. Okay, so it's exactly the triangle inequality. Oh, what other properties can you think of, right? So if you any other property? How about product? Okay, product of Lipschitz continuous. Say L1 and L2. So I'll make it similar. So if you have L1 and L2 Lipschitz continuous functions. You say something? Is it Lipschitz continuous? So imagine taking f1 into f2 or f into g, f into g minus f into g, fx gx minus fy gy. I know both of these are so. Both of these are Lipschitz continuous. So what's the relation? Fx gx minus fy gy is a relation that is has with fx minus fy and gx minus gy. Anyone? I'd like you to open up a bit, otherwise it'll just be a monologue. Is there an inequality? Can I say this? Or, or do I need some additional assumption? So it turns out that it cannot be just L1, L2 Lipschitz. Okay, so if you additionally have that these are bounded, then you are fine. If they are not bounded, so product of bounded, and that's easy to see. If I have to put this inequality somewhere, I need to know that f and g are themselves not going to become infinite. Okay, so I'll leave that as homework for you, but it turns out it's not very difficult. So bounded, yes, if they are bounded, then you can say. By the way, I mean I have a more detailed in my more detailed course on optimization. I would probably have the proof there sitting, so you can use that if you want. So this yes is less than equal to L1 into L2, but also the bound of the function. I'm going to leave that as kind of homework for you to look at. Okay, so two Lipschitz continuous and bounded functions also Bounded as homework, please try and prove. Okay. Any questions so far? So Lipschitz continuity is important. Yeah,
Sir,
yeah.
does the constant L have to be the same throughout the domain or can it be variable?
Um, does the function have to be? So can you repeat again?
So as in like if we say that the function f is Lipschitz continuous,
Mhm.
so can L be,
L be constant.
huh,
That's a good point. So sometimes we say in in this region it is Lipschitz continuous with L. In another region it is Lipschitz continuous with some other L. So you can put a domain for each domain you can have a different L. That's possible, but you have to explicitly state that. Is that okay? That's a good point. Is that clear? Hello.
yes sir.
Okay. So we'll see some examples. So there's a notion of a Lipschitz smooth function as well. So instead of talking about the function, now we talk about the vector of functions. Oh, sorry, vector valued function, which is a gradient. So a function f is called smooth if its gradient is Lipschitz continuous. Basically, we are saying that there's a limit on the rate of change of the gradient. F of x, the gradient of f of x, sorry, the norm of the gradient of f of x minus f of y less than equal to L times the norm of x minus y. What does this ring bells about? Probably rings bells about rate of change of the gradient, and rate of change of the gradient we all know is connected to what? The rate of change of the gradient is connected to its Hessian, right? So good. So roughly, what does it mean? Just taking on the discussion from Lipschitz continuous, we are saying this roughly means a function has an upper bounded double derivative, but that's the same as saying upper bounded curvature. Okay. Uh, that in strong convexity, the rate of change of the function is at least so much, is about lower bounded curvature. I mean, it should be at least there should be some gap above a quadratic, right? This is exactly the other way. It's saying it's an upper bounded curvature. So in the case of strong convexity, we probably would have had something like this. We would have said the function's Hessian um, at all points is say greater than equal to some lambda. Okay, so what I should be actually talking about is curvature. So therefore, I'll look at okay, V transpose Hessian inverse. Sorry, V. This is the lower bounded curvature. By analogy, we should probably have something similar here. We should say V transpose the curvature. Basically, along any line, if I look at the curvature, this should have this should be less than equal to say L. So something like this I would expect. Anyone wants to comment? Okay, so what does this mean pictorially? Pictorially, let's get the understand. Right, so basically, we are saying um, something like this. we are saying that this strong convexity, we are saying that the function cannot be too flat. Actually, let me just use a different color here. Let's switch to. So strong convexity, we are saying the function cannot be too flat. I should just use a different color here. Okay, so this is upper bounded curvature, the one in blue. And one in red is a lower bounded curvature. So here, in the case of strong convexity, that is the function cannot be too flat. So we are putting that red curve to indicate that there's a limit to how flat it will be. Whereas the blue curve is saying that the function cannot be too curved upwards. Okay. So let's take this discussion forward. We can basically write the same thing differently, right? We can say, okay, this is what I had written. So you're saying that the gradient is upper bounded. So this rate of change of the gradient is upper bounded. It's saying the Hessian has this upper bounded L. That's the blue part here. But you can say the same thing in the case of a strong convexity. Strong convexity was about the Hessian being upper bounded, say by. So we'll typically use M. Sometimes you'll use theta, lambda, whatever, right? So this is what we mean by strong convexity. So they are in some sense complementing each other. They may appear to be opposing, but we are just saying that two lower bound. I mean, there's a lower bound and upper bound, so they can coexist. Let me know if there are questions. So now almost everything we have defined, you'll start finding analogies. So, we had at least 3 definitions of strong convexity. One was in terms of Hessian. This is exactly what we're seeing now. We had a definition of strong convexity in terms of the first order approximation, there being a quadratic cap. But also in terms of the monotonicity of the gradients or subgradients, we had a definition. All of those could be, you'll actually find a complementary definition here. So, so if a convex function is smooth, so this is called smoothness. Okay, you say Lipschitz continuous gradient is the same as saying it is Lipschitz continuous is called smooth. So function is smooth, then now we are saying fx plus this linear term plus a quadratic term is upper bounding fy, right? This is a quadratic upper bound. Okay. Whereas for strong convexity, what did we have? Can anyone recall? This is a quadratic upper bound, yes. What did we have in the case of strong convexity? We had a quadratic lower bound, exactly what we showed in the previous slide, right? This is same idea. The red curve is a quadratic lower bound, and the blue curve is a quadratic upper bound. Let's just keep this picture in mind. Okay, so we can complete this picture as well, and that was f of y is greater than or equal to f of x. So everything looks the same, but that the quadratic lower bound will have a different L, or you'll have M by 2 times. Constant will change, that's it. So obviously you expect M to be less than L. Is that correct? M should be less than equal to, or ideally strictly less than, right? Okay, so is this clear? Then let's take examples. If there are questions, let me know. We'll be doing lots of examples. Okay, if there are no questions, one question I have for you: what would be an example of function which is both strongly convex as well as Lipschitz continuous? Can you think of one? Let me ask you this question. Can you think, is there a function which is both strongly, can you come up with one? Lipschitz smooth, which means Lipschitz continuous gradient, right? So be very specific. So Lipschitz continuity was slightly different, okay, which was only about the function. Now we're talking about gradient. That's where you have some analogy or some complementarity with respect to strong convexity. So what would be an example? Simplest example. So can I take x square? In fact, that will come in the next slide. Right? X square. You take the x square, then the Hessian. Think in terms of Hessian, you can terms of quadratic lower bound, whatever, right? The double derivative is 1. 1 is lower bounded by 0.5 and upper bounded by 3 or any other number, right? The simplest example. Okay, so let's look at this. Fx equals x square. So gradient is 2x. Hessian it's x plus 2. Then you can easily say 1 is less than equal to. Yeah, mistakenly mentioned on the previous slide. The Hessian is 1. But it's 1 is less than equal to 2, which is less than equal to 3. So think of this 1 as the m and this 3 as the l. So this is yeah, for strong T, whereas the L on the right hand side is for Lipschitz smoothness. Any questions? It's an example. So I'm just unfolding the same thing. You can also think of it as, um, prove it using the rate of change of the gradient. Okay, so same thing, basically get the same Lipschitz constant too. Now is fx equals x raised to 4 Lipschitz smooth? If x is fx equals x cubed by 3 Lipschitz smooth, we're studying the latter to begin with. Is a latter Lipschitz smooth? Yes. So let's consider the case of fx
We'll have
equals,
to constrain the domain for this, right?
okay, yeah. So if you look at the Hessian, it's like 2x, right? Or if you look in terms of the change rate of change of gradient, x square minus y square is less than equal to L times x minus y. Does that exist in L? Your answer is not unless you constrain the gradient. You're right. Require constraining the domain. So you can basically expand this to identify in what domain is it. Lipschitz smooth. Right, so this is basically absolute value of x square minus y square, absolute value of x minus y into x plus y. So the question is, for what values is less than equal to L times x minus y? So the answer is if, when is it? If x plus y is less than L, right? So for what will you do for any x plus y? Now what does x plus y less than L mean? Basically, if x is bounded, y is bounded, then obviously x plus y is less than equal to some bounded value, right? So for any let's say absolute value of x less than alpha, I'll have absolute value of x plus y is less than equal to 2 alpha, which could be thought of as L. So this is an example of constraining the domain. Okay, so any questions or comments here? Okay, so the overall assessment is that globally, you know, this case of x cubed by 3 is certainly not globally Lipschitz continuous. Globally, this is not Lipschitz continuous, though it can be locally. So only functions of asymptotically at most quadratic growth can be smooth globally, right? I mean, that's what we tried showing x square here. This is an example. You could come up with a lower bound and upper bound both. Quadratic growth. But then now I have a question. What about x raised to 4? Any thoughts? So if you have quick response, you can let me know. Otherwise, I'll be leaving it as homework. Is x raised to 4 strongly convex? Surprisingly, it is not, right? So I would like, yeah, you can think a bit more about it. Study it as homework. Let's study a few more examples. Now, one question I have, I mean, understanding of Lipschitz continuity and smoothness. Does one imply the other? Does Lipschitz continuity imply smoothness and vice versa? Anyone? Are they connected? Are they totally disconnected? Let's take some example. Actually, we'll see more examples to appreciate this. So let's say f dash x is, so I'm given a hypothetical function f whose derivative is the absolute value of x. right? And now ask the same question: is the f dash x minus f dash y, which is basically the absolute value of the absolute value of x minus absolute value of y, is it less than equal to L times absolute value of x minus y? Okay, so well, it turns out that not difficult to analyze. Yes, it is, because this holds, right? This holds. The difference of the absolute value is less than equal to the difference absolute value, the difference of the values. So f is Lipschitz continuous with L equals 1. That's fine. Is Lipschitz. Okay, so f its rate of change of f dash is what we are bounding. Lipschitz continuous with L equals 1. But what about f double dash? Does it exist? F double dash x. Well, you don't, I mean, honestly need f double dash. You could talk in terms of rate of change of the, all right. So here what we did was f dash, sorry, this is, just wanted to be clear. When we say f is Lipschitz, f dash is Lipschitz continuous, okay? It doesn't even exist everywhere. Then what about this f dash is Lipschitz continuous? That is f is basically smooth. Okay, f doesn't exist, which is fine. Now how about the Lipschitz continuity of f? Okay, so we talked about the Lipschitz continuity of f dash x, rate of change of f dash. What about Lipschitz continuity of f? We could talk about the Lipschitz continuity of f dash, even though it doesn't exist everywhere. But yeah, I would like you to think about Lipschitz continuity of f. But let's going back to the f double dash. It's not differentiable everywhere, but it's differentiable almost everywhere. Okay, it is differentiable almost everywhere. Okay, so such functions are called differentiable almost everywhere. Another example is norm of x, one norm of x. Right? So one norm of x is also differentiable almost everywhere. Okay, so it's not that no you need double derivative to exist everywhere to be able to talk about Lipschitz smoothness. That's Lipschitz continuity of the derivative. Okay, let's continue this discussion. Is every subquadratic function Lipschitz smooth? So what we mean by subquadratic is an example. Fx is the absolute value of x raised to 3 by 2. It's subquadratic, right? So is this Lipschitz smooth? If you consider it on a closed set x such that 0 is in x, is it Lipschitz smooth? So the gradient of f dash x at infinity at 0 is infinity, right? Like we can just verify that quickly. f dash x. Okay, so the gradient of f dash x, this function, is infinity at x equals 0. So let's consider this specific example. Three by two, x raised to half. This is of course for x greater than 0. Okay, and in that case f double dash x is 3 by 4, x raised to minus half. And in such a case, is this function smooth? Well, it is not globally smooth. It's not smooth if 0 is in x. Right, we have a problem. But smooth in bounded and closed interval not containing 0. I mean exactly what we said earlier. But now getting more specific. Was someone trying to say something? So it is not globally smooth. However, the it's also not smooth if 0 is in x. The domain. But it's smooth in a bounded and closed interval which is not containing x. Why is bounded and closed required? I'd like you to think. Not containing 0. Okay. Yeah. Don't want to spend too much time with these. This is the whole goal is to get you familiar. It'd be nice if you think a little bit more. But let's talk about this closed and bounded Lipschitz continuity and smoothness of closed and bounded functions. Okay, there's some interesting result. I've actually put it down in my notes, theorem 1.4.1, my advanced notes. So if a function is continuously differentiable almost everywhere, it is also Lipschitz continuous. So we said that many, like one norm of x is differentiable almost everywhere. It turns out that it's also Lipschitz continuous. So Lipschitz continuous is something we get a little uh, easily. Okay, of course for Rn function going from Rn to R. And now we look at some other interesting properties. For a bounded subset of Rn, then this is the property. Let me take some examples as we go. So f is continuous. Oh, this we know too many of these. Okay, so let's say x, e raised to x, all these right are continuous. That has a subset which is f is differentiable almost everywhere. That's what I was talking about some time back. Now what is this? Let's take examples again. And let's see if some of the examples we discussed earlier are fine. Yeah. X, in fact, not just x, absolute value of x, e raised to x is differentiable almost everywhere. The derivative of absolute value of x is not continuous everywhere. You have to consider suitable subgradient at 0. Okay, but this is fine. The examples. Okay, these are examples. Let's take the third case, which is in green. F is Lipschitz continuous. Now let's start seeing if it starts shrinking. Have we lost something? Have we lost any of these? Well, e raised to x seems to be fine. Is Lipschitz continuous? Yes. Lipschitz continuous. Is absolute value of x
Yes.
Yes, in fact it's exactly the same. F is differentiable almost everywhere. The same as F is Lipschitz continuous. Sorry, I should just use the same color. All of these are the same. So let me just use a blue color here. The same. Okay. But let's now move to the third category. F is continuously differentiable, which means that the function itself, its derivative itself is continuous. Now, we have a problem with absolute value of x. That won't qualify. Right? So absolute value of x basically goes out of the window. Right? Whereas all of these so far were okay. Yeah, but we don't have absolute value of x qualifying this criterion. What else is e raised to x seems to be fine, right? X can be fine. In fact, f dash x, which is x such that f dash x is absolute value of x, which is what we saw in the previous, right? That belongs to all these categories. Okay, so I'll put it back here as well. I mean, I'm expanding all these sets. F dash x, f x such that f dash x is absolute value of x belongs to both these categories. Oh, so it has shrunk, and we have dropped absolute value of x. And it turns out that this is the same as saying that the gradient of f is continuous. Okay. And then a subset of that happens to be that the gradient of f is differentiable almost everywhere. Now we have a problem with absolute value of x. Okay, that you can't even talk about differentiable almost everywhere. Okay, so let's go to the next, which is this one. So what are the examples? Well, e raised to x stands here as well. So does x stand here, but we have lost absolute value of x. In fact, we can also drop f dash x as absolute value of x. Okay, and that is the same as saying that f is smooth. So this last category has two names, almost differentiable almost everywhere, and is the same as saying f is smooth. Okay, so we can quickly depict this in the form of this kind of concentric circles. The red one is at the top, the largest subset, and then keeps shrinking. I took some examples, but can take a lot more examples. So this on closed and bounded functions, there's some connection. I mean, I'll ask this question: what's the relation between Lipschitz continuity and smoothness? So Lipschitz continuity and smoothness you can talk about in the case of it being continuously differentiable. Sorry, the function on closed and bounded, right? For closed and bounded functions, we can talk about this relation, but not in general. Any questions on this slide? In practice, you'll find that most smooth functions will also turn out to be Lipschitz continuous, right? Because we may be often dealing with this closed and bounded functions. Okay. So you can think of this again the other way, right? Implies if f is smooth, then closed and bounded, then it is continuously differentiable, then it is Lipschitz continuous, then it is continuous, and so on. Okay, right. And recall that a function is Lipschitz continuous if the norm of the subgradient is bounded, so that we have found some other equivalent conditions, right? So yeah, closed and bounded subset of Rn that f is Lipschitz continuous. Now this is interesting. The last point on a closed and bounded subset of Rn, f is Lipschitz continuous is a superset of F being convex. So now I can just draw a slightly different picture. So we have also brought in this additional condition, okay, here. This pink, so far we had, if you go back to the previous slide, we didn't have the pink, right? We had the red. So F is continuous was the largest one. Now we are saying that if that F is convex and subset of Rn, right? On a subset of Rn is closed and bounded. If you want, else let me just make it correct. So on close on subset of Rn, which is closed and bounded. Yeah. Okay, I'll make that correction. Subset of Rn that is closed and bounded. Okay, so this is like a interesting summary of the pictorial summary of what we are discussing. Now we can talk a little bit more on strong convexity, Lipschitz continuity, and smoothness. So recall that if you had a strongly convex, I had a function which was convex, you could make it strongly convex by adding this mu by 2 norm x square, or rather, if that a function is strongly convex if there exists a mu such that even after subtracting mu by 2 norm x square for a non-negative mu, you still have convexity. If we could recover strong convexity from convexity, okay. So, right? Recall, we could construct that was a motivation for regularization. A strongly convex function by adding a regularizer. That's the basic idea. The question is, can we do something similar for Lipschitz smoothness? Can we make a function Lipschitz smooth? Any suggestions? We were basically adding a regularizer to increase its curvature. Any thoughts? So question is, can we make a function Lipschitz? When I say make, I mean construct a Lipschitz smooth function, a given function which is not Lipschitz smooth, which may not be. Any suggestions? What will you do? The hint is, instead of decreasing curvature, subtract a regularizer, decrease curvature. I mean, this is a question I have. But if it's not convex, like, see, given a functions, but if the function itself is not convex, what do you do? I mean, we need something more. This may not be sufficient. Right? You may say, okay, I'll take a gx, right? And instead of adding, subtracting mu or whatever, I'll add, say, an L by 2 norm x square. Is this a solution? Does this not require some assumption or property of G? I mean, should G be convex at least? Please help me. I mean, it'll be nice if you chip in here. Okay, so that's the question we are trying to ask. Is there a similar result for Lipschitz smooth functions? Okay. Anyone before we move on? So it turns out that there is a very similar analog, but it requires convexity. Okay, so the answer is yes. If G is convex, we can do such a transformation. So I mean Lipschitz, while we note that Lipschitz smoothness did not require convexity, right? I mean we just defined it without convexity. But if you want to make a transformation, then convexity again becomes handy. So yeah, see how ubiquitous convexity is. It's all pervading. I mean, I give you many reasons why it's ubiquitous. It's like take the last layer of a neural network, you'll have convexity there. Okay, so I hope you're able to appreciate this. Okay. Okay, so this is the idea. A function f is Lipschitz smooth if there exists a constant L such that L by 2 norm x square minus fx is convex. So this is different. Yes, now, so it's not exactly this. Okay, it's not just adding. It's subtracting gx and adding to it L by 2 norm x square. So function f is Lipschitz smooth if there is an L such that L by 2 norm x square minus fx is convex. Right? And in fact, there is a duality between the two. We'll not get into the duality aspect now. If a function f is strongly convex and g is convex, then the function f plus g is strongly convex, right? But if a function, and we know that if a function is Lipschitz smooth, sum of two Lipschitz smooth functions also Lipschitz smooth. Okay, that's something we dealt with earlier. So right. So I'm going to leave you with some homework now. This is going to be more important homework than the homework I've given you so far. Can we use all of these properties and prove some of these, right? ML loss functions, that's our goal. Logistic loss, does it have some properties? Is it Lipschitz smooth? Yeah, what's the proof sketch? I may not do proof as great detail as I did for convexity and strong convexity, but give some thought to it. Logistic loss, how do you prove is Lipschitz smooth? Hinge loss, is Lipschitz continuous? Okay, no direct claim about Lipschitz smoothness. Obviously, it's not. There may be issues of differentiability, not everywhere, right? Multi-class logistic regression, it's Lipschitz smooth. I mean, it's follow up in some sense from logistic loss. Least squares is Lipschitz smooth and strongly convex. So this is a very rare combination that you get both x square like, right? So this is least squares is both Lipschitz smooth and strongly convex. Now when you do L2 regularization, you have Lipschitz smoothness and strong convexity. L2 regularization itself, right? L1 regularization is only Lipschitz continuous. And now when you add these like regularization, so far we didn't add the regularizers. Now if you start doing L1 regularized logistic loss, what do you get? You get Lipschitz continuous. L2 regularized logistic loss is strongly convex and Lipschitz smooth. And L1 regularized hinge loss is Lipschitz continuous. Okay, convexity will be there in most places. I've skipped convexity per se, but I only brought in strong convexity and Lipschitz continuous / smoothness. L2 regularized hinge loss on the other hand is Lipschitz continuous and strongly convex on a bounded set. Okay, and this is finally L2 regularized least squares lasso is Lipschitz smooth and strongly convex. And then L1 regularized least squares is Lipschitz continuous and strongly convex. Of course, there's a lot I've stated here. I'm going to just please mull over these. Okay, I'll end here. So I'm just going to. I've given you the statement. Just mull over these. At least get a hang of some of these. I won't say it won't prove, but yeah, and roughly prove. That's also fine. Okay, and let's discuss further on Thursday.
Sir, I had a query
Yeah.
regarding the assignment.
Okay. I think assignment we should have the TAs. Maybe we can discuss on. You can post a query. Um, you can ask the query right now, but it'll be good to have the TAs. Yeah. Go ahead, please.
Like in the programming part, in the